Okay, hello and welcome everybody to another new video. So in this video, I will be teaching you how to calculate nCr mod p efficiently using Fermat's little theorem. So this nCr mod p, right, it's a very powerful function. It appears across many problems, especially in coding interviews and programming contests. So it is useful and it is to your advantage to know how to calculate nCr mod p efficiently. Sometimes when people don't know of this method, they actually use dynamic programming to compute the whole Pascal triangle to calculate nCr mod p, which is quite time consuming and tedious. So I will be teaching you on how you can actually use Fermat's little theorem to calculate nCr mod p. So without further ado, let's get started. So I'll start by defining what is nCr. So nCr essentially denotes the number of ways we can choose r items out of n items. Okay, so this is the math formula to calculate nCr. So you can take some time to read it. So I'll just give a quick example problem. So given 10 labeled apples in the basket, how many ways are there to pick 6 apples? So what differentiates a set of 6 apples from another set of 6 apples is the fact that all the 10 apples, right, have a label on them from 1 to 10. And that is how we actually differentiate from a set of 6 apples from another set of 6 apples. And the answer to this question is simply 10 choose 6. Right? Because there's 10C6 ways to choose 6 apples from 10 apples in the basket. Okay, it's pretty straightforward, pretty intuitive. Now we're going to move on to modular arithmetic. So modular arithmetic is quite intuitive as well. For instance, a plus b mod m is simply congruent to a mod m plus b mod m, the whole thing mod m. And the same can be said for the negative sign and the multiplication sign. Oops. Now, can we extrapolate what we have here, okay, to the division one? So can I say that a over b mod m is congruent to a mod m, b mod m, the whole thing mod m? Well, turns out the answer is no. Now, why not? So I'm going to show you why that's not possible with a counter example. So let's say our numerator is 10 and our denominator is 5. Okay? And 10 over 5, right? 10 over 5 is equal to 2, because 10 divided by 5 is 2, right? So 2 mod 3 is simply 2, hence the left hand side is 2. Then 10 mod 3 is 1. So this part here is 1. And 5 mod 3 is 2, hence we get half on the right hand side. So half mod 3 is simply half. So we notice that the left hand side is not equal to the right hand side. 2 is not equal to half. Hence, this particular equation does not hold and hence is not true. So now how? So how do we actually calculate a over b mod m? So now let's go back. So a over b mod m, right? We notice that a over b can be rewritten as a times b negative 1. Okay? Because we know that 1 over x is equal to x to the power of negative 1. So what we can do is we can simply rewrite this as this. A times b to the power of negative 1. And now our question now pivots into how do we actually compute b to the power of negative 1 mod m. Because this here is a multiplication sign. So we can actually use this equation to help us calculate a over b mod m. Okay, so now the question is, how do we calculate this b to the power of negative 1 mod m? And there's a special case, is that m, this particular m, is a prime number. So how can we exploit this to our advantage? How can we exploit this fact, the fact that m is a prime number, to help us calculate the multiplicative inverse of b? turns out we can actually use Fermat's little theorem. So what is Fermat's little theorem? So this line, okay, essentially encapsulates what Fermat's little theorem is. So a to the power of p is congruent to a modulo p, where p can be any prime number, 2, 3, 5, blah blah blah. Now, assuming a and p are relatively prime, and when I mean that they are relatively prime, I mean that the greatest common divisor between a and p is 1. Meaning that they don't share any common factors greater than 1. So assuming that a and p are relatively prime, we can actually derive this result. A to the power of p minus 1 is congruent to 1 modulo p. Now, let's use this result. Obtained from the previous slide, and let's manipulate it a bit. So we're going to multiply both sides by a to the power of negative 1. So a to the power of p minus 1 times a to the power of negative 1, congruent to 1 times a to the power of negative 1 modulo p, and eventually we will get this. A to the power of p minus 2 is congruent to a to the power of negative 1 mod p. We are going to use this result to help us calculate the multiplicative inverse of b. So using this result that we have obtained from the previous slide, a over b mod m is equal to this, right? So this is what we have obtained from the previous slide. And what we can do is we can substitute a to the power of p minus 2 into here. So in this case, a in this case, right, will be b, and p minus 2 will simply be m minus 2. And ta-da! We are done with calculating a over b mod m. Now, going back to nCr, so this is the full formula of nCr, right? N factorial over r factorial times n minus r factorial, where p can be any prime number. So usually p is about 10 to the power of 9 plus 7. So it's quite common in programming contests and coding interviews, such as leak code. So to calculate n choose r mod p is simply n factorial mod p. So n factorial mod p times r factorial to the power of p minus 2. So this r factorial, because this r factorial, right, is the one that's at the denominator, right, is the one that we're actually dividing. Hence, we raise it to the power of p minus 2 using what we have obtained earlier on from here. And same thing, n minus r factorial to the power of p minus 2, because of the result we have obtained earlier from here, okay, from this particular expression. And then finally, we multiply everything together and mod p. So essentially, that's how we calculate n choose r mod p. Okay, so now what we're going to do is that we're going to apply this nCr mod p, this whole expression, into code. And I'm going to show you how we can actually implement this whole nasty math expression into C++. So without further ado, let's get started. So first, we'll need to include the necessary libraries. So usually I like to include c++.h because it already includes all the libraries that I need. And then I'm going to include namespace std because this will allow me to shorten my code drastically. And then I'm going to create some type definitions. So first, I'm going to start with vector in vi. And then I'm also going to create another type definition, long. So essentially it's just shorthand notation so that it allows me, so instead of typing long, I can just type ll. So again, it helps me increase my code efficiency. Okay, so now I'm going to create my main function and I'm going to make sure that everything works. So hello world. Okay, so now everything works fine. So now what I want to do, right, because if we were to take a look at expression, right, we have something raised to the power of p minus 2, like r factorial to the power of p minus 2, n minus r factorial to the power of p minus 2. So obviously it makes sense to implement a function that will allow me to raise a to the power of b in logarithmic time, preferably log p time. And turns out we can actually use exponentiation by squaring. Okay, exponentiation by squaring. So if you're not sure what that means, feel free to go and search it up online because I don't want to dive too much into how this works because that's not the scope of this video. But if you're interested, I can make another video on this particular method. Okay, so let me just implement this exponentiation by squaring function, which allows me to compute a to the power of b in logarithmic b time. So LLEXP, because this is going to return long, and then LLAB, so I'm going to return the power of a to the power of b. So first, if b is equal to 0, right, I know that I have to return 1. I have to return 1 because anything raised to the power of 0 is just 1, and I know if b is equal 1, I can just return a, because anything raised to the power of 1 is simply the number itself. Now I'm going to compute half by exp. I'm calling this function again using recursion, and then I know the answer is simply half times half. So let's say if I have 4, right, let's say if b is 4, right, I can compute a squared times a squared, which together, when they are multiplied together, they'll get a to the power of 4. So, and then I'll need to mod it. So let me just define p 1, 2, 3, 4, 5, 6, 7, 8, 9, half times half, and then let me just mod this. And then if b is actually an odd number, right, I will need to actually multiply a itself, because 5 over 2 is still 2. We need to multiply the number itself one time into the final expression. So ans multiply this equal by a, and then I'll need to modulo this answer. Finally, I can return ans. So this will be my final answer, and let me just verify that this works by printing, let's say, 2 power of 5. So I should see 32 on my console, and if I were to print 4, I should see 16. Okay, good. That means our exponentiation function works. Now, if we look at nCr, right, we also need to calculate factorial, n factorial, r factorial, n minus r factorial. So it will make sense to use dynamic programming to calculate the factorials, to compute and store the factorials. So I have a vector f. So this vector will be used to store the factorials. So I'm going to put everything in this initialization function, and then I'll just give f initial value. So let's say 10,000, 0, and then the factorial of 0 is equal to the factorial of 1, which is just 1, and then I can create a for loop, and then I'm going to run it all the way. I'll set fi equals to I times fi minus 1, and this whole thing mod p. Okay, so essentially I'm using dynamic programming to help me compute the factorials, and then I need to call the initialization function first before doing any prior calculations, and then I think that's it. So let's check, make sure that our factorial is working fine. So f at 6, so the factorial of 6 should be 720. Okay, that's good. Now finally, let's calculate void nCr. So nLLR. Oh, I need to return a long as well. Okay, so now we're just going to implement whatever we have here. So first we're going to return n factorial mod p. So f n, okay, which is n factorial mod p. We already modded p here, so there's no need to mod p again. Multiply this thing by r factorial to the power of p minus 2. So f to the power of factorial of r, right? R factorial to the power of p minus 2. So we can use this function a to the power of b. So exp, we're going to raise the factorial of r to p minus 2. And then we need to kind of mod this to ensure that this expression does not overflow. And then we're going to multiply this whole expression by n minus r factorial to the power of p minus 2. So exp factorial of n minus r to the power of p minus 2. And this whole thing, we're going to mod it again. And that's it. That's how we calculate nCr. So now if I were to calculate nCr 42, I should see 6 and 52 Now it works. So to really verify that this program works, right, let's try solving an actual lead code problem. Okay, so I found this problem on lead code. Essentially, we're just going to compute Pascal's triangle. So usually people will use dynamic programming, right, to actually compute the whole Pascal's triangle. But we're going to try something a little bit different. We're going to use Fermat's little theorem. Okay, basically all this nonsense, and we're going to try to solve Pascal's triangle using number theory. Okay, so without further ado, let's get started. So first we have one input, which is number of rows, and I'm going to denote that as n. And then I'm just going to create a for loop that runs for every row. So, and then because let's say on the 4th row, right, we have 4 numbers, on the 5th row we have 5 numbers, so we know that the number of numbers on that particular row is determined by the number, by the row number. So j is equals to 0, j less than or equal to I, j plus plus. We're going to see out nCr ji, and I'm going to see out n line here, and I'm going to see out a spacing here to kind of keep the numbers spaced apart from each other. So let's try 5, and it doesn't work because oops, ij. Okay, let's try again. 1 2 1 1 3 3. Okay, can. That's good. Let's do from 0 instead, because we want to have 1. That's 1 1 at the top, right? So we need to have 1 1. So we're going to start from 0 instead. And boom. Okay, we're done. So now I'm just going to copy all the code that we have here, and I'm going to paste it inside here. And then I'm going to copy my definitions all the way at the top. And then I'm going to copy my for loop into this main function. Lastly, I'm going to copy the init function into here. Okay, so now we're going to have a vector of vector ints. So we're going to have a 2-dimensional vector. I'll call this the answer. And then I'll call this answer.pushback and the I.pushback nCr ij. I don't need to see out. Instead, I need to return the answer. And then oh, I need to assign as well. I need to give the answer vector initial values of n, and I'm going to create n instances of empty vectors. Let's try. Oh, let's call this n. Okay. Okay, looking good, looking good. Let's try to submit this. Okay, done. So we have solved this question, and we have verified that the nCr program that we just wrote using Fermat's little theorem works. So that's all for this tutorial, and I hope you have enjoyed. Let me know if you wish to see any more video tutorials or any topics you want me to cover. Thank you.